LLM agents are powerful, but their memory systems are hitting a hard wall. Every time an agent needs to remember something, most frameworks ask the LLM itself to summarize, compress, or index past interactions. That turns memory management into a recurring generative workload. You burn tokens, you add latency, and you inevitably lose traceability. Details get merged, temporal updates get blurred, and the original interaction traces disappear behind generated abstractions. On the flip side, you can just dump the raw history and do flat lexical or dense retrieval. It preserves the original text, but flat retrieval gets confused by semantically similar traces from different sessions, and it completely fails when the answer requires connecting evidence distributed across multiple interactions. Effective agent memory needs structured, query-conditioned access without sacrificing provenance. That's exactly what Zero-Mem delivers. It's a framework that eliminates all LLM calls and all LLM token consumption from memory operations. Construction, organization, routing, retrieval, and calibration run entirely token-free. The only time an LLM is invoked is for the final question-answering step. Zero-Mem works by keeping the raw interaction history intact and building two non-generative, complementary views over it, a relational entity context graph and a temporal hierarchy. Every memory operation routes through these structures, fuses them based on the query, and filters the results deterministically before the LLM ever sees the data. Let's start with a relational view. Zero-Mem applies a standard, non-generative named entity recognition model, like spaCy, to each context unit. It constructs a graph where nodes are either detected entities or context units. Edges represent two things: co-occurrence, where an entity appears in a context unit, and adjacency, where context units appear next to each other in the conversation. The weight of an entity context edge is simply the normalized frequency of that entity within that context. Adjacent turns are linked to preserve local continuity. Crucially, this doesn't generate semantic triples or infer relationships. It just records what actually appeared together. When a query arrives, Zero-Mem aligns query entities to graph entities using dense embeddings. It then propagates activation through relevant co-occurrence sentences. An entity scores high when it co-occurs with an already activated entity in sentences that match the query. These propagated activations, combined with dense context priors, form a query-specific reset vector. That vector feeds into a personalized PageRank algorithm with a damping factor of 0.6. The resulting stationary node scores rank the context nodes. Exact lexical matches for names, dates, or values then fine-tune this ranking. This is how Zero-Mem recovers cross-session, entity-relational evidence without a single LLM call. But graphs alone don't preserve order or session state. That's where the temporal hierarchy comes in. Zero-Mem organizes traces into four granularities: turns, windows, episodes, and local spans. Turns are atomic utterances. Windows group adjacent turns for short-range context. Episodes cluster windows into coherent event regions based on semantic continuity and session boundaries. Local spans preserve the immediate neighborhood of a selected turn when surrounding context is needed. Retrieval here is coarse-defined. It starts at the episode level to find relevant event regions, narrows to windows, drills down to turns, and only expands to local spans when necessary. Each unit retains its original text, source identifier, and metadata. This view explicitly maintains temporal locality, conversational flow, and session-level state, which flat retrieval completely misses. At query time, Zero-Mem doesn't just pick one view. It builds a lightweight, deterministic query profile containing the subject, keywords, expected answer type, temporal cues, and session boundaries. This profile dictates routing. Relational queries, like those asking about entity connections or cross-document reasoning, weight the graph view higher. Local queries, like those asking about what was said in a specific session or turn, weight the hierarchy higher. Both views are executed, but their normalized scores are fused using a routing coefficient. After fusion, Zero-Mem runs an evidence closure step. It supplements the top candidates with relational bridges from the graph and neighboring turns from the hierarchy, deduplicates them using shared unit identifiers, and produces a compact evidence set. Before the LLM even processes that set, Zero-Mem applies deterministic evidence calibration. It filters out candidates that violate provenance or query boundary constraints, then ranks the rest by subject, temporal, and answer type compatibility. Once the LLM generates a preliminary answer, a second deterministic calibration step checks it against the retrieved evidence. It validates evidence support, verifies answer type and format, and applies extractive normalization or list pruning if needed. If the LLM's answer is already supported and well-formed, it's kept. If not, it's corrected using only the retrieved traces. No generative loops. No extra tokens. Encoder computation is handled separately, keeping the memory pipeline strictly token-free. So does this actually work under pressure? On the LoCoMo benchmark, which tests long-term conversational memory across multi-session interactions, Zero-Mem outperforms all baselines in average F1 and BLEU1, with particularly strong gains on temporal and open domain questions. On HotpotQA, under extreme context lengths up to 448,000 tokens, it consistently achieves the highest F1 scores, proving it can locate and connect distributed evidence even when drowned in distractors. The efficiency gains are where it really stands out. Compared to the fastest memory-optimized baseline, Zero-Mem cuts memory operation latency by 57.6%. More importantly, it consumes exactly ZERO LLM tokens for memory operations. Even the most token-efficient generative systems still burn hundreds of thousands of tokens per query. Zero-Mem shifts that cost to lightweight encoder inference, graph traversal, and deterministic filtering, which are orders of magnitude cheaper and faster. Ablation studies confirm the architecture's design. Using only the graph view or only the hierarchy significantly drops performance, proving they're complementary. The graph connects distributed evidence. The hierarchy preserves the local context needed to interpret it. Evidence closure and deterministic calibration each provide measurable gains by completing and refining the retrieved set. Performance also stabilizes quickly. Retrieving 5 candidates per query captures nearly all available signal, with diminishing returns beyond 10. Zero-Mem demonstrates a clear paradigm shift. Structured agent memory doesn't need generative abstraction. By keeping the original traces intact and using deterministic, query-conditioned routing over relational and temporal views, you get traceable, high-fidelity memory that scales without burning tokens. The code and implementation details are already open, and I highly recommend digging into the paper if you're building agents that need to remember things without paying the generative tax. Thanks for watching.